This first slide demonstrates the simple linear regression model. For any plot of data points, a line can be formed that estimates the input and output of the data. Correlation measures the degree of linear relationship among variables. If the line is a very good estimate of the data, it will have a correlation with a magnitude close to 1. Conversely, if the line is a poor estimate of the data, the correlation will have a magnitude close to 0. As you can see in the graph, the line towards the bottom of the graph has a very weak correlation, while the line at the top of the graph has a very strong correlation. In other words, if the line seems to fit the data well, it will have a relatively high correlation. An example of real-world application using linear regression and correlation can be seen in the third lab experiment in the Design of Aerospace Experiments course. In this lab, the goal is to measure the lift and drag on an airfoil inside of a wind tunnel. In order to measure these values, static pressure taps made up of tubes and pressure transducers must be placed along the areas in which we want to record this data. Without getting too much off topic, in order to successfully measure these pressure values, each pressure transducer must be carefully calibrated. When calibrating these pressure transducers, we used a system involving a hand pump to control the water and a barometer. The pressure transducer is attached to the barometer and the DAC to acquire the data. At various levels of water in the barometer, height and voltage output were recorded. After plotting these data points, we were able to form a line of best fit to our data that could now be used to get true pressure outputs for each input of voltage acquired by the DAC. The second slide exemplifies exactly what the software on the computer was doing as it calculated our line of best fit. This process is known as the method of least squares. This method incorporates testing different lines to fit the data while drawing squares from each data point back to the line, and finally summing the areas of each square. After testing various lines and summing numerous square areas, the line that yields the smallest summation of square areas will be chosen because it has the strongest correlation to the data. The last slide is an example showing the difference between a small and large amount of variability inherent in the regression model. When sigma squared is large, the data points will be quite spread out about the true regression line. And when sigma squared is small, the data points will be very tight about the true regression line. However, as you can see in the plot shown, just because there is a large amount of variability, it does not mean the line chosen is a poor estimation of the data.